everyone. In reaction today, the reaction is Birch reduction. So today I am going to discuss about the Birch reduction. The Birch reduction is a chemical synthesis which we can use to convert benzene and other aromatic compounds to 1,4-cyclohexadiene. For this reaction we need sodium or lithium in liquid ammonia, and we also needed ethanol or methanol or tertiary butanol which act as a source of hydrogen, and we have to maintain a quite below temperature like -80 to -30 degrees Celsius. So here in this scheme you can see that benzene is reduced to cyclohexadiene 1,4-cyclohexadiene in presence of sodium or lithium in liquid ammonia in ethanol at very low temperature. So here you remember the liquid ammonia is using as a solvent and ethanol means any alcohol that using as a source of hydrogen. Now let's understand the mechanism of this particular reaction. Let's understand the mechanism of Birch reduction. So initially in presence of ammonia, sodium loses one electron, it gives you Na plus and one electron. Now this electron act as a nucleophile to the aromatic system. So here you can see that electrons attacks to the aromatic system, and here one anion and opposite to the anion at 4 position a radical forms. So this is called benzene radical anion. Now if you count the pi electrons, you can see there are total 7 pi electrons are here in the benzene radical anion. Now this benzene radical anion act as a strong base. So here benzene radical anion can abstract the proton from the alcohol. Now here you can see that this protonation takes place here in this carbon. But here in the opposite position here still the radical present. So now this radical will abstract electron, or electrons will attack to this radical. It's a free radical mechanism, and here the radical is now converted to the anion. Now similar fashion this radical will now get protonated from the alcohol, and now we are getting 1,4-cyclohexadiene. Now from this reaction mechanism we have to remember a few important points, that in this reaction the electrons which is generating from the sodium it act as a nucleophile and which attacks to the benzene ring to generate the radical anion. So here one radical and here one anion is forming. So this is called benzene radical anion. And benzene radical anion is a strong base, so it can abstract the proton from the alcoholic OH, not from the ammonia, because ammonia, that hydrogen is not strong acidic enough that it can be donated to the anionic side. So that's why using of alcohol is important for the Birch reduction. Now let's understand when benzene has some substituent, what is going to happen in the Birch reduction. So in this particular reaction, it's a benzoic acid. So COOH, this act as a electron withdrawing group. So here in the when electron withdrawing groups are present, the protonation will take place in this carbon, the carbon which is directly attached with the COH group. Now with respect to this one, the second protonation will take place. Now when we are taking a electron donating group like methoxy here, so the first protonation will take place in this carbon, the carbon which is the adjacent of the carbon where the carbon is attached with the electron donating group. So here first protonation will take place, means first radical anion will form in this carbon, so it will abstract the proton from the alcohol. Then with respect to this one, the second protonation will take place in the 4th position. So here you can see presence of electron donating group and the electron withdrawing group. Birch reduction is giving different kind of 1,4-cyclohexadiene. Now here I am going to discuss about a common mistakes. If we have taken chlorobenzene and the reagents we have taken sodium, ammonia, same low temperature we have maintained, here we will not get the Birch reduction product, because if you have noticed the reactants carefully, here you can see we are not using alcohol. So for Birch reduction you need the alcohol, because when the radical will form, the benzene radical anion will form, that has to abstract the proton from alcohol, not from the ammonia. So that's why when you are using sodium ammonia at low temperature in chlorobenzene, we don't get Birch reduction product. Here a different mechanism takes place and we get a different product. Now when we take chlorobenzene and add sodium ammonia at low temperature, it gives you benzene intermediate, and then NH2 minus attack either side of the benzene and we get aniline. So here sodium and ammonia give you sodamide. Now sodamide is used as a strong base which remove this chlorine from here and then a double bond from here. Then finally this is a triple bond. This is called benzene. And then NH2 minus also can act as a nucleophile and can attack either side of the benzene and give you the aniline. So it follows a mechanism that is called the nucleophilic aromatic substitution. Nucleophilic aromatic, there are two different types of nucleophilic aromatic substitution. One is the elimination addition mechanism and second one is the addition elimination mechanism. So here it follows the elimination addition mechanism. First chlorine leave, elimination take place, then the nucleophile attack. So that's why it is called elimination addition mechanism. Now here you have noticed that for this particular reaction we have used sodium and ammonia, but we are not using alcohol. So if we use sodium ammonia with alcohol, it gives you a Birch reduction product, not the nucleophilic aromatic substitution product. Now another common mistakes, that if we take simple benzene and if we add sodium and ammonia, it will not undergo nucleophilic aromatic substitution, even it will not undergo the Birch reduction. Because to undergo the nucleophilic aromatic substitution you need a halogens, because it will leave and then it will form a benzene. So CH bond, this hydrogen cannot break. So that's why no benzene will form, no NH2 will form. So that means it cannot undergo nucleophilic aromatic substitution. And it will also not undergo Birch reduction because we are not using alcohol here. We are just using sodium and ammonia. So there will be no Birch reduction, there will be no nucleophilic aromatic substitution reaction. So to undergo the nucleophilic aromatic substitution reaction, you need chloro or bromobenzene. You have to treat with sodium and ammonia. And if you want for a Birch reduction product, you have to take sodium and ammonia with the methanol. Now I think you understand the reactions properly and when and how to use sodium and ammonia for the different reactions. In similar reaction condition, the partial reactions of alkynes take place. Now usually we know that if we use palladium hydrogen, alkyne completely reduced to alkane. But we can also perform a partial reduction using sodium ammonia. So partial reduction means alkynes will convert to alkene, not alkane. So here you can see the hydrogen addition takes place at anti position, like these are the trans alkene is forming. Now if we want to make a cis alkene from alkyne, we need Linder catalyst. Sodium ammonia will give you the trans alkene from alkyne and Linder catalyst give you cis alkene from alkyne. So if you want to know more details about the Linder catalyst, I have already designed a video. That link will be shared in the comment section. This video will be helpful for your study. So thank you for watching this video. If you have chemistry related queries, contact chemistry.affinity@gmail.com. Thank you.